All right, today we are diving into something really cool, the absolute frontier of manufacturing. I mean, we're talking about creating materials on a scale that is so small it's almost impossible to even wrap your head around. We're going to explore how to craft matter, literally atom by atom, using a fascinating technique called laser ablation. So let's just start with a fundamental question, a real mind-bender. Think about the smallest thing you can possibly imagine. Now picture something thousands of times smaller than that. How in the world do you build something when your building blocks are smaller than the very light you'd need to see them? It sounds like it's straight out of science fiction, but this is a very real challenge that scientists are tackling right now. To get to the bottom of that big question, we first have to ask, why? Why would we even want to operate on this incredibly tiny scale? Well, it all comes down to shrinking matter down to its most basic, and often its most powerful, form. And the answer is nanoparticles. These are the ultra-tiny building blocks for all sorts of future tech. You know, we're talking about things like super-targeted drug delivery systems in medicine, way more powerful and efficient computer chips, or even creating entirely new materials with properties we've never seen before. Seriously, mastering how to create these is like learning the alphabet for a whole new technological language. Okay, so how do we actually do it? How do we make these things? Well, one of the key methods is a process called laser ablation. This is where scientists use a super-focused beam of light to literally carve out these microscopic particles from a larger material. It's just an incredibly clever solution. The process itself is, surprisingly straightforward when you break it down. So first, you take your source material, let's say a little piece of gold, and you stick it in a liquid. Then, you blast it with an incredibly powerful, really short pulsed laser. This blast is so intense, it vaporizes atoms right off the surface. It's like a microscopic, hyper-precise sandblaster. And then, as those atoms cool down in the liquid, they start to clump together, forming brand new nanoparticles. Simple as that. And what you get at the end is something called a colloidal solution. Now, that might sound technical, but it's actually pretty simple. It just means you've got these shiny new nanoparticles floating perfectly inside the liquid, not sinking to the bottom or clumping up. They're just suspended in there, stable, and ready to go.
And look, this isn't just me talking. This comes straight from the scientific paper itself. I know, it looks a little dense, but check it out. It describes how laser irradiation leads to fragmentation of solid material in the form of nanoparticles, which remain in liquid that surrounds the target. See? That complicated sentence is exactly the four-step process we just walked through.
But here's the really cool part. This isn't just blasting away randomly. Scientists basically have this whole control panel they can use to fine-tune the final product. By tweaking the laser's power, its wavelength, its color, how long the blast lasts, and even the type of liquid they use, they can precisely control the size and shape of the nanoparticles they're making. It's like being a microscopic sculpture with a light beam for a chisel. Now, like any piece of tech, laser ablation isn't perfect. It has some absolutely incredible strengths, but it also has some key weaknesses. It's a fantastic tool for sure, but it's not without its challenges. So on the one hand, the huge win here is purity. Because you're only using a laser and a simple liquid, you don't need a bunch of extra chemicals or additives. That means the nanoparticles you get are incredibly pure and, as we said, highly tunable. But, and this is a big but, there's a catch. The very nanoparticles you're working so hard to create start to get in your way. They form this little cloud in the liquid that can actually block the laser from hitting the target, sucking up its energy and slowing the whole operation down. And, the source material just lays it out there, plain and simple. As more and more of these particles get created, they start to shield the target. And the result? I'm quoting directly here. This overall leads to a reduction in ablation rate. So basically, the process becomes a victim of its own success. So, what's the bottom line here? It's pretty straightforward, really. Laser ablation is a powerful, remarkably pure way to create the building blocks for future tech, but it comes with a built-in speed limit. The more stuff you make, the slower the process gets. It's a classic engineering trade-off. You get amazing quality, but you have to sacrifice some speed. And all of this leaves us with this incredible, wide-open question. We now have this amazing tool that lets us forge the raw materials for future technologies with unbelievable purity and precision. So as we get better and better at this, what should we build first? What are the biggest, most important problems we should be trying to solve with it? That's definitely something to think about.